First of all, we should all thank Jake for his fast grading for your exam. Otherwise, that wouldn't be the case. You wouldn't get your grade. So thank you, Jake, for grading those that fast, the exam that fast. I have the statistics for the exam, yet again, the laptop decided not to work today. Okay, so we're gonna have to switch with the projector in here. So if the laptop decided to work at any point, I'll show you the statistics for the exam. Again, the average is so expected. This is what happens every semester. Chapter 5 and 6 always are more challenging than the first two chapters of this course. Then on exam 3, the average will go a little bit more up than exam 2. And that's for the exam. I can't show the statistics right now. So what we're gonna do, we still have three slides from chapter 7. Then we're gonna get started with chapter 8. So for this one here, so arrange the following in an increasing order of the ionic radius. So I'm going to give you a minute or so, and then I'm going to start talking about this. So we're talking about sodium in here, we have sulfur, and Cl.
Oh, those are
Just because S has more protons, right?
Yeah. No, less.
Less protons. So it means, oh, that's right. Because it's smaller.
Okay.
I can do this.
Okay. So first of all, we have the Cl. We're comparing Cl minus to S2 minus to sodium plus. The first thing that you should remember that anions are bigger in radius than cations. Okay, and the anion that has a higher charge, that means it gained more electrons, so it has more electrons out there, so the radius is bigger. The anion with the higher charge is going to have the biggest radius. So in this case, the anion with the highest charge is sulfide, S2 minus, so definitely it's going to have a higher radius or a bigger radius than Cl minus. Then sodium plus. Always cations are smaller than anions, so sodium is the smallest, which may be the right answer in this case. Now, one more topic that we didn't discuss yet is the isoelectronic ions. Isoelectronic ions, by definition, isoelectronic, the word iso means equal. So isoelectronic, that means it has the same number of electrons. Those are the ions which have the same number of electrons. By definition, let's start, for example, all of these series, N3 minus, O2 minus, F minus, Na plus, and Fg2 plus, all of these are isoelectrons. They have the same number of moles. Let's look for nitrogen. Nitrogen has 7 electrons. 3 minus, that means it's gained the 3 electrons, so it has 10 electrons. Let's look to the oxygen. Oxygen has 8 plus 2, that's 10 electrons. Fluorine group, 9 electrons plus 1 electron, 10. Sodium, 11 electrons minus 1 because it has a plus, 10 electrons. Magnesium, 2 plus, then now it is 10 electrons. So all of these are isoelectronic. Jake? Maybe. Okay, so this is the definition of isoelectronic. So whenever I ask you, are they isoelectronic, whether it is a molecule, we're going to talk about molecules later on, but as we're talking about molecules or ions, this is what it means. So I'm going to give you a minute or so to solve this one.
These two.
Okay, so which of the following are isoelectronic with sodium ion? So first of all, sodium plus, so that means it has 11 minus 1 electron, so it has 10 electrons. Oxide, we know that oxygen belongs to group 2, to group 6, so, and it's gonna lose, when it is an ion, it's gonna lose it's gonna gain 2 electrons. So we're talking, when we say oxide ions, we're talking about O2 minus. So it has 8 plus 2, that means it has 10 electrons. Now the sulfide, when we talk about sulfide, sulfide ion, it belongs to group 6A, that means it's gonna gain 2 electrons. So we're talking about S2 minus, and I have it 14 plus 2, that has 16 electrons. Fluoride, when we talk about fluoride ion, it belongs to group 7A, that means it's going to have F minus. It has 10 electrons and 9 electrons plus 1, so that's 10 electrons, which make sodium isoelectronic with oxide and fluoride, so A and C, so 2 is the right answer. I'll give you just 1 minute. Okay, so now this is the end of chapter 7, and we're gonna start with chapter 8. And chapter 8, it talks about chemical bonding. So we talked before about the atom, the electronic configuration, all these details about the atom. Now we're gonna look when the atoms make bonding. Okay, so we're gonna look how they bond, what's gonna happen at this stage when they bond together. First of all, we're gonna see the bonding, what kind of bonding. Second, we're gonna look at the shape of the molecules. Are the molecules flat? Are they tetrahedral? We're gonna talk about the geometry, the 3-dimensional geometry, and we're gonna talk about the molecules themselves, whether they are the geometry of those molecules. So, by now we know that the two main bonding that we talked about in this class, we talked about ionic bonding and covalent bonding. And ionic bonding takes place when a group 1A and 2A, exception hydrogen, react with or they form compounds with the non-metals of a group 5A, 6A, and 7A. The bond is ionic. And we talked about that in chapter 3, in chapter 2 when we were talking about ionic. Okay, and now the computer is ready, so we can go back to iClickers and everything. Okay. Okay. So, since we have the computer back, this is the statistics for the this is the statistics for the exam. This is the average of the class. Most of you are in this area. Um, it depends how much you scored in exam one. If you are in this part, you better talk to me, or we need to talk to each other about this in here. And that's but the average of the exam is okay. It's the same as any average years before. Let's go back to what we were talking about, which is talking about chemical bonding. So we said that an ionic bonding takes place when group 1A, 2A, except hydrogen, that doesn't include hydrogen, make a bond with the non-metals of a group 5A, 6A, and 7A. The bonding is ionic. Now the covalent bonding takes place between the non-metals of a group 4A and 7A between each other. What does that mean? Carbon with fluorine, oxygen with fluorine, fluorine with fluorine, Cl with Cl, Br with Cl, sulfur with chlorine. All of these gonna be covalent bonding. All of those gonna form a covalent bonding. Now, what's the difference between ionic and covalent bonding? So in ionic bonding, the electrons are lost and gained. That means, for example, in sodium chloride, which is an ionic compound, sodium loses the electron and Cl minus gains that electron. And the only thing that keeps the Na with the Cl minus is the electrostatic interaction, which we talked about using Coulomb's law. This is the only bonding between them. But the electron is lost by the cation and it is gained by the anion. For covalent bonding, no, it's sharing. The electron is not lost and it's not gained. The electrons is somewhere between A and B. Let's say this is a covalent bond. The electron is in between. They share the electrons. Now this share can be equally or non-equally, and this is what we're going to talk about when we're going to talk about electronic activity, when we're going to talk about the polarity of the bond. But mainly, neither A lost the electron nor B gained it. It's in between. It's a sharing. So covalent is sharing. It can be equal sharing or non-equal, and ionic is losing and gaining of electrons. Now, all what we're going to talk about from now on is the covalent bonding, because we already covered the ionic bonding when we were talking about balancing the molecular formula in calcium chloride, and we talked about those, the acid-base reactions, and all of those where we were talking about ionic compound. From here on, we're going to talk about covalent bonding and molecular compound. Now, covalent bonding, again, it's the attraction of the two nuclei for the same electron. Usually, we represent the bond between two molecules by a dash, and we call this a single bond. Or we can, when we put two dashes in between, that means this is a double bond. And when we put the three, that's a triple bond. Okay. An example of a covalent bond is H and Cl. HCl is a covalent bond. How did I know that? We said that all group 1 and 2, when they have compounds with the non-metal of 5, 6, and 7A, it's ionic except for hydrogen. So hydrogen with any of the group 7A, 6A, 5A, the non-metal is going to be a covalent bond. And this is how we represent it. H bond Cl with those lone pairs. Now what we're gonna learn today is to know or to figure out how many bonds are there, how many lone pairs are there on the chlorine, and how we figure that out. How we can draw this structure based on the rules which are Lewis rules, which is the scientist that put the rules for drawing molecular structures. So the first rule before, there are many rules until we get to the Lewis structure. The first rule is that any atom inside any molecule, inside any combination of molecules, it has a big tendency, or its aim is to get to the octet rule, which is 8 electrons around it. So in all of the compounds that we're gonna see, we're gonna make sure that each atom in that compound has 8 electrons by bonding. And this is why, as I said before, all group 7A or 6A or 5A, we said that they lose or gain electron. In the covalent bond, they share electron or they do bonding to get to the same electronic configuration as a noble gas, which is 8 electrons in the valence shell. This is what the octet rule is stating, that all the atoms have a big tendency that they share electron or they do bonding to have 8 electrons around them in the outermost shell. There are exceptions for this rule, and we're gonna learn some more exceptions. Those 3 atoms are the ones that wouldn't have the octet rule. They don't need 8 electrons around them. Hydrogen, it just needs 2 electrons around it, so it will do 1 bond. Beryllium, it's gonna need 4 electrons around it, 2 bonds. Boron, there are 3 bonds, it needs 3 bonds. There are cases where it obeys the octet rule, and there are sometimes that don't. So boron, you're gonna see sometimes it's gonna have 4, and sometimes it's gonna have 3 bonds around it. Now, later on, we're gonna see that some atoms will exceed the octet rule. They will have 10 electrons around them, or 12 electrons around them. We're gonna learn that later on. But for the moment, most of the atoms in a molecule, they prefer to have 8 electrons, exception for that, hydrogen, boron, and beryllium. Now, the valence electron, how are we going to represent those groups? So let's say I have an element from group 7A. So I know for sure that the electronic configuration is NS2, NP5. This is what we learned in chapter 6. So the box notation is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so this notation, I'm going to change it into what we call it the Lewis structure. So the Lewis structure of that element in group 7, the way that we do it, we start with 1 electron at a time. 1, 2, 3, 4, 5, 6, 7. Did everybody see what I did? Should I repeat what I did? Yes? No? Yes? Okay. So this is X, which belongs to group 7A. I'm going to start with 1 electron. Each dot represents 1 electron in the valence shell, not in the core. We're not talking about the whole electron. We're talking only about the valence. So this belongs to group 7A, so it has 7 electrons around it as a valence. 1, 2, 3, 4. Now, after the 4, I begin pairing. 5, 6, 7. Okay? Now, if we look at this, it exactly represents the electron configuration. Those 2 paired electrons represented by this. Those 2 paired electrons, it's represented in here. 2 paired electrons and 1 unpaired electron. Okay, we're gonna do the same. This is the Lewis dot structure for any atom as it is from group 7A. Now we're gonna go to 6A. We know that it is NS2, NP4. So the box notation, like a box. 2, 3, 4. So again, 1, 2, 3, 4, 5, 6. So it exactly represents the electronic configuration, the valence electronic configuration. 2 unpaired, 2 unpaired, 2 paired, 2 paired, and 2 unpaired. We call this, those two, we call them lone pair of electrons. So from now on, when I tell you there is 2 lone pairs or 3 lone pairs, so this is, we have, the 7A has 1, 2, 3 lone pairs. So we call those lone pairs. Now, this dot, mainly, that's one electron and the atom needs another electron. This is where it's going to do the bonding. This is where it's going to bond to something else to form a bond, and now it's going to have the 8 electrons. Now we're going to go to 5A, so it is NS2, NP3. Two, 3, so it is X, 1, 2, 3, 4, 5. And it exactly, as I said, it represents the electronic configuration, 1 lone pair and 3 unpaired electrons. Those 3 unpaired electrons, they would be ready to do 3 bonds. So group 5A will do 3 bonds. Group 6A clearly is going to do 2 bonds because it has, most of the time. Definitely there are exceptions. We're going to talk about those later on. 7A, 1 bond. Okay. Now we're going to go to 4A. Group 4A, it's NS2, NP2. So X, 1, 2, 3, 4. Now if we look to the representation, to the electronic configuration, and to this one, in this one we have a paired electron, right? Which you don't see in the representation I did. And this is what we're going to learn later on. Those 4 unpaired electrons, they are there due to hybridization, which we're going to talk about later on in chapter 9. So, group 1A, 2A, 3A, 7A, 6A, 5A, they all, their Lewis dot structure represent exactly the electronic configuration in terms of the number of paired electrons and unpaired electrons. 4A is, because it does a hybridization, because it undergoes a hybridization, where NS2 and NP2, they kind of combine with each other to form the same orbital, which we're going to talk about in chapter 9. Okay? Now for group 3A, it's NS2, NP1. One, 2, 3. Again, we're going to talk about the hybridization of this later on. So group 3, the non-metals of group 3, they're going to do 2 bonds. Now group 1A and 2A, we're not interested in as Lewis structure because they form ionic compounds. So we're not going to go to the Lewis structure. We're using this to look at the molecular, how they're going to form covalent bonds. Okay, does this make sense? Any questions before I go any further about those? Yes?
How many bonds did you say were in 4A and 3A?
4A? 4 bonds because it has 1, 2, 3, 4. So it's going to form 4 bonds. So any unpaired electron by itself, it's going to make a bond. Each one of these is going to make a bond so that it has the 8 electrons around.
So you said 2 bonds for 3A?
For 3A, 3 bonds. Okay, so now, after knowing how to draw kind of the Lewis structure for each one of the atoms, we're going to go a step further. So, until now we didn't talk about electronegativity. Electronegativity is the ability of the atom to attract the electron toward it, more toward it when we have a covalent bond. So let's say I have A and B, and this bond is covalent. Electronegativity, let's say we're talking about the electronegativity of B. If B is more electronegative than A, it's going to attract the electrons more toward it. Okay? So electronegativity is the ability of the atom to attract electrons toward it in a covalent bond. Now the trends of electronegativity, those numbers that you see in this periodic table in here, are the numbers of electronegativity, or what we call the chi, which represent the electronegativity. The higher the electronegativity, that means the more the ability of the atom to attract the electron to it. So if you look, you can see that the electronegativity is increasing this way, and as we go this way in the periodic table. Okay? And that's the trend of electronegativity. So the electronegativity increase going up the semi group, and as we go from left to right in the periodic table. Okay? And that's going to be very important because we're going to base our molecular structure on the electronegativity. As you can see, that hydrogen is a little bit more electronegative than group 1A and 2A. It is somewhere in between boron and carbon in electronegativity. This is why it is in this part of the periodic table as it is listed there. Okay. Now, how are we going to determine the Lewis dot structure? Now, this handout that you have with a worksheet on the back. Now, for the moment, you can only, after this lecture, you're going to only be able to write the Lewis structure. Later on, we're going to learn how to do the Vesper model, the geometry, and the angle, later on in this chapter. For the moment, I already summarized for you what are the steps. It's a longer process to get to the molecular, how to draw the Lewis structure of molecules. We're going to practice as much as we can today how to do that. So the first thing, let's say I give you, for example, CO2. We're going to wave CO2. F2 is not a good example. So CO2, the first thing that you have to think about, what is the central atom? Is oxygen the central atom? Is carbon the central atom? So this is the first step, determine the central atom. The central atom is the atom with the lowest electronegativity. So we looked at the periodic table, we know the trends of electronegativity. It goes this way and this way. So carbon is less electronegative than oxygen. So I know for sure that carbon is the central atom and the two oxygen gonna be connected to the carbon. Now, most of the time the molecule is gonna look symmetrical. In the case of CO2, that's the plane of symmetry. There are two exceptions for symmetrical, which is N2O is one of the exceptions. Hydrogen, if we have a hydrogen in the atom, it's always going to be terminal. Hydrogen always going to be terminal, even if it is more electronegative than the central atom. Less electronegative than the central atom, it's going to be terminal. Group 7A, most of the time they are terminal. That means at the end of the molecule. There are some exceptions when we're going to talk about the expanded octet rule. But most of the time, hydrogen and all group 7A are going to be terminal. And the central atom is the carbon. Now, in case of acids, always connect the hydrogen to the oxygen. Always do that. Always, in case of acids, connect. And I'm talking about oxoacids. That means acids that have oxygen. If they don't have oxygen, so you can't do anything about it. Now, the next step is to count the total number of valence electrons. So, and I'm going to call it N total. So, I have two oxygens. Each belongs to group 6A, so they have 6 valence electrons. And carbons belongs to group 4A, that means it has 4 valence electrons. So that's a total 12 plus 4, that's a total of 16 electrons. Now, if I have an anion, something like NO3 minus, that means the whole compound gained an electron. So I would add an electron to here. If I have something like X plus, that means this whole X gained lost an electron, so I would put minus 1 electron. We're gonna do cases like this, but just a heads up for you. So the second thing, we count the total number of electrons. Now after that, we connect the central atom by one bond to the terminal atoms. Now, with that in mind, that means 1, 2, 3, 4, there are 4 electrons in bonding because each bond represents 2 electrons. So each one of these, each bond represents 2 electrons. So I have 1, 2, 3, 4. So I'm gonna subtract those 4 electrons from the total. So minus 4, so I have total of 12 electrons. So my next step is to take those 12 electrons and begin putting them as lone pair on the terminal atoms. I'm gonna repeat what I said. After we subtract the number of electrons in bonding, we're gonna take that number and begin putting them as lone pairs on the terminal atoms as needed. What does it mean as needed? Until the octet rule, that's what as needed means. So I'm gonna put 1, 2, 3, 4, 5, 6, 7, 8. So I can't put any more. So those are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So those are the 12 electrons from what is left. So I put 2 lone pairs on each terminal atom until the atom has 8 electrons. I stop. Now, when I looked at this structure, we said that for any Lewis structure, any atom in that structure should have 8 electrons. So I looked at the oxygen. It has 1, 2, 3, 4, 5, 6, 7, 8. It has the octet rule. This oxygen has the octet rule, but the carbon does not. The carbon only have 1, 2, 3, 4. 4 electrons. So it needs another 4 electrons to have the octet rule. So now what I'm gonna do, I'm gonna borrow those lone pair and put it as one bond because each 2 electrons is one bond. And then I'm gonna borrow those 2 electrons and put it in bonding. So I'm gonna have a double bond with 2 lone pairs on here and 2 lone pairs on there. Now, so we're borrowing the electrons. We're not getting electrons from nowhere, okay? So the total electrons should not exceed the 12 electrons at the end, 16 electrons at the end. So how did I figure out that I can do a double bond for carbon and oxygen? There are some atoms that can do double and triple bond and some atoms cannot. And here is the list. Carbon, nitrogen, phosphorus, sulfur, oxygen can make double and triple bond. So carbon, nitrogen, phosphorus, sulfur, and oxygen can make triple and double bond. Either double, they also can do single bond, but they can do both. Halogens do not form double bonds. Hydrogen cannot form double bond. So keep that in mind. And this is a state what I did before, forms a single bond between the central atom and each surrounding atom. Then after that, if you need more electrons for the central atom, just borrow it from the terminal atoms. Okay. Okay, so now we're gonna start with some examples. Now all these rules are summarized for you in here, and actually they are more in detail. Okay, let's start with N2. Try to draw the Lewis structure of N2. gonna do now is I'm gonna open the iClicker for attendance since I didn't take any iClicker for the first 2 slides. So press any letter, it doesn't matter from A to C. Okay, so the first thing is determine what is the central atom. In this case, it's N2. There isn't a central atom, so it's going to be nitrogen connected to nitrogen. There is no central atom. It isn't three atoms in this molecule. It's 2. So definitely they're going to be connected to each other. Okay. The second thing, the total number of valence electron. Both nitrogen definitely belongs to group 5. So 2 times 5 electrons. So I have total of 10 electrons. I have 1 bond, so 1, 2 minus 2 electrons in bonding. So that's end me up with 8 electrons. Now I'm gonna put those 8 electrons as lone pairs on the terminal atoms. In this case, both of them are terminal atoms. It is a homonuclear atom. So 1, 2, 3, 4, 5, 6. Now this nitrogen have 8 electrons. I can't add more lone pairs to it. 6, 7, 8. Now clearly, this one in here has the octet. It has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Now this one has 1, 2, 3, 4. So it needs 4 more electrons. So I'm gonna borrow those 2 electrons, put it in bonding, and those 2 electrons and put it in bonding. But before I go any further, I have to double check if nitrogen can do double or triple bond. So I go back to my list. It says carbon, nitrogen, oxygen, phosphorus, and sulfur. They can form double and triple bond. So now I end up with triple bond. So this is the Lewis structure of N2. So every time you're given a molecule, you have to do all these steps. Okay, so let's begin with an iClicker about the Lewis structure. So I'm going to stop that in here and start. We already did the CO2 as an example, so would you like to do it? Or would you like to skip it? Do it? Okay. So let's do it. I don't mind. And I'm going to stop it at 2 minutes.
She's just dropped. Oh no, I lost her. She's upset about a lecture thing though.
Okay. gonna stop it right here, check what you think. 97%. Great. Okay, so first, the central atom, the one with the lowest electronegativity, we know that the electronegativity increases this way in the periodic table. Carbon is here, oxygen is there, so this is lower in electronegativity. Carbon gonna be the central atom and the two oxygen around it. The total number of valence electrons, carbon group 4, so 4 electrons. Oxygen group 6, 2 times 6 electrons, that's total of 12 plus 4, 16 electrons. 1, 2, 3, 4, minus 4 electron in bonding. So I have 12 electrons. Those I'm going to put them on the terminal as needed. That means until I get to the octet rule. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The carbon, both oxygen has 8 electrons, but both oxygen each has 8 electrons, but the carbon does not. So I'm going to borrow those 2 electrons and 2 electrons. I know the carbon and oxygen can do a double bond. So this is the right Lewis structure. Let's do some more. NH3. I'm going to stop it at 130.
How many unpaired electrons? Nitrogen has 2 unpaired electrons. So I'm going to stop it at 130 and check what you think. So I have 87% for B. B is the right. So first of all, what is the central atom? Hydrogen can never be the central atom. So that's clearly make the nitrogen the central atom, and I'm going to connect it to the 3 hydrogens. The total number of valence electrons, I have 3 hydrogen. They belong, definitely hydrogen belongs to group 1, so 1 electron, plus nitrogen, nitrogen group 5, so that's total of 8 electrons. Now I have 1, 2, 3, 4, 5, 6, minus 6 electron in bonding. So I'm going to end up with 2 electrons. Now, usually the rule is put the electrons that are left on the terminal atom, but I can put it on hydrogen because hydrogen does not need 8 electrons. All what it needs is 2 electrons, and 1, 2 it has 1, 2, 1, 2. So in this case, whatever left, I'm going to put it on the central atom, which is right there, which makes this the right Lewis structure. Okay, let's do some more. Again, I'm going to stop it at 110. It should be water's unbalanced. It's not weird, right? So I'm gonna start it at 1K. And check what you think. And I have 8, 95%. 8 is the right answer. Okay, wait a minute. We still have time. According to AT&T, it's 8:49. So we still have 1 minute. So oxygen is the central atom because hydrogen can never be the central atom. The total number of valence electron oxygen belongs to 6 plus 2 times 1, that's total of 8 electrons, minus 4 electrons in bonding, that's total of 4 electrons. I'm going to put them on the central atom. And enjoy your long weekend, and I'll see you Wednesday.